is quite easy to calculate the kinetic energy of an object moving in a straight line, which we know is half mv square. And what makes it easy is the fact that every particle of this body is moving at the same velocity v. So making use of this formula is quite straightforward. But recall from the last lesson, the linear velocity of each point in a rotating body is different. That is, points that are closer to the axis of rotation have lower linear velocity, and as you move away from the axis of rotation, the velocity of the points keeps increasing. So using this formula is not a good choice because it is designed to be used when the velocity is constant for every point in the body. So how do we calculate the kinetic energy of rotating bodies? Well, to do so, let us take a rotating body, say the rotating blade of a helicopter, and try to work around it. As a first step, we will divide up the helicopter blade as a collection of very small masses, each having their own speed basis how far or near they are to the axis of rotation. Then, if we can find the kinetic energy of each such particle, we can simply add them up to find the total kinetic energy of the blade as a whole. So let us say this is mass m1, this is m2, this is m3, this is m4, and so on, and we list each particle till we reach the last one, and let us call it the nth particle. And we also mark their respective velocities, say they are v1, v2, v3, and so on till we label the velocity of the nth particle as vn. Then we can say that the kinetic energy of this particle is half mv1 square, this is half m2 v2 square, this is half m3 v3 square, till we reach the last particle or the nth particle whose kinetic energy would be half mn vn square. Now, if we add up the kinetic energy values of each of these particles, we get the total kinetic energy of the entire blade as this. And the shorthand for writing this long expression is sigma half mi vi square, where mi is the mass of the ith particle and vi is its speed. And we say that the I value changes from the first particle, that is particle number 1, to the last particle, that is particle number n. In fact, we should add the last term, that would be half mn vn squared over here as well. Now, while this expression seems quite simple and neat, the problem is how do we find the velocity of each of the particles? Well, there is an easy solution to this. That is, we use the formula v is equal to omega r and substitute it over here to get k is equal to sigma half mi omega ri square, which equals half sigma mi ri square times omega square. So you see, all we have done here is to present the velocity vi of the ith particle in terms of the angular velocity omega, that is the same for all particles, and the perpendicular distance of the ith particle from the axis of rotation. Now, this quantity that I have put in brackets is very interesting because it tells us how the mass of the blade or the rotating body is distributed about its axis of rotation. That is, if more mass is situated farther away from the axis of rotation, this value will go up. On the other hand, if it is situated nearer to the axis, it will go down. So this quantity is called the rotational inertia of a body, or some books term it as the moment of inertia, and denoted by the symbol I. Also, it is a constant for a given body about a particular axis of rotation. In other words, the axis of rotation must be specified if the value of I is to make sense. So we cannot say that the I value of this body is, let us say, 120 kilogram meter square. You would have to say it is 120 kilogram meter square about this axis, simply because it could be a different value about some other axis of rotation. As an example, if this body is rotated about this axis of rotation, it would have a certain rotational inertia value, while if it is rotated about this axis, it'll have a different value. And if you pause for a moment and think, in which case would the value be higher, what you'll find is that it would be higher when the axis of rotation is this. Simply because you can see here that there are more number of particles at a larger distance from the axis of rotation than in this case. So you see, the distribution of mass around the axis of rotation changes the I value quite a bit. So let us write this equation in terms of I, or the rotational inertia, and that would become K is equal to half I omega square. And remember that omega should be expressed in radians here, and then the SI units for I will be kilogram square meter. So this equation gives a kinetic energy of a rigid body in pure rotation, and you could say that it is the angular equivalent of the formula half mv square that we use for objects undergoing pure translation. So let us take another example where we get a feel of the idea that the rotational inertia of a body is not only about the body's mass, but also how the mass is distributed. So imagine rotating a longish heavy rod, say a pole, around its central axis, that is this, and then around the axis at 90 degrees to the rod at the same angular velocity omega. And what you'll realize is that even though both situations involve the same mass, this rotation is easier than this one. And the simple reason is that here the mass is distributed much nearer to the axis of rotation than this one. And therefore, the rotational inertia of the rod is much larger in this case, giving it a higher kinetic energy. That is more difficult to control by you, or in other words, puts more mechanical strain on your muscles. Now, the next question that should come to your mind is, how do we calculate the rotational inertia I itself? So, if a body consists of just a few particles, it is easy to find the I value. All you need to do is take the mr square value of each particle and then sum them up. As an example, if the rigid body has 3 particles only with masses m1, m2 and m3 at a distance r1, r2 and r3 about the axis of rotation, the I value would be m1 r1 square plus m2 r2 square plus m3 r3 square. But if the rigid body has a lot of particles that are not really countable, say a continuous object like this, then what we do is replace this sum with an integral and find the rotational inertia of the body as I is equal to integral of r square dm. Remember, integral is nothing but summation only, quite the way we do here. The only difference is that it is a technique used when quantities we are dealing with are not countable. So, to understand this better, let us take an example where we will find the rotational inertia of this rod that has mass m and length L about this axis of rotation. Now, we know that the rod has a large number of particles at varied distances from the axis of rotation. So, it is quite impossible to find the mr square value for each particle. So, what we will do is write an expression of the rotational inertia of a mass dm that is at a distance r from the axis of rotation, and that would be r square dm. Now, we will sum the rotational inertias of every small mass across the length of the rod by integrating this expression using this equation. So, we're basically integrating along the x-axis. And therefore, we must relate the mass dm of the rod to its length dx along the rod to convert this expression into something we can actually integrate. Now, if the rod has a uniform mass, then we can say that the mass per unit length would be its mass divided by its length, or m upon L. And then for length dx, the mass would be this multiplied by dx. So we can now go ahead and use this in place of dm and x instead of r. And if we integrate from one end to the other, that is from x is equal to minus L by 2 to x is equal to L by 2, which basically means we've included all the elements of the rod, what we get is I is equal to integral x square m upon L dx as you integrate from plus L by 2 to minus L by 2, or I is equal to m by L integral x square dx, which when you simplify, you get I is equal to 1 by 12 ml square about this axis. Now, if you're asked what would be the rod's rotational inertia I about another rotation axis, say through the left end, we can simply assume origin to be this point and then integrate from x is equal to 0 to x is equal to L. And what you get is I is equal to integral x square m upon L dx as x changes from 0 to L. And when you integrate, what you get is I is equal to 1 by 3 ml square. And you can see that this rotational inertia is 4 times this one. Now, we can get the same result, that is this, by using a powerful and easier technique by using something what we call the parallel axis theorem. Now, do not get scared by this heavy sounding theorem, because all it says is that if we already know the rotational inertia I of a body about the axis of rotation, say here we know the I value about this axis, then the rotational inertia about any other axis of rotation that is parallel and at a perpendicular distance h from this axis can be given as I is equal to I known plus mh square. So you see, the condition is that the axis about which you wish to find I should be parallel to the axis about which I is already known. And if you want a proof of this theorem, I have given it in the description below. So if we use this theorem to find the rotational inertia here about this axis, what we get is I is equal to I known, that is this, plus mh square, where h becomes this distance. So putting the known values, we get I is equal to 1 by 12 ml square plus m into half L square, which equals 1 by 12 ml square plus 1 by 4 ml square, which equals 1 by 3 ml square. And you see, we get the same result, but a lot quicker. So if you want to master this topic, I'd suggest you head over to this playlist that covers all aspects of rotation, rolling, and torque really well. And if you like this lesson, do give a thumbs up, and I will see you in the next lesson.